In this class, we are going to show that center of group is actually a subgroup of G. Now, what exactly center of group is? So, center of group is collection of all those elements of G that commutes with all the elements of G. So, what is the difference between center of an element and center of a group? Center of an element is restricted to element A only. So it says it is collection of all those elements of G that commutes with A. But on other side, center of G says it is a collection of all those elements of G that commutes with every element of G, right? So it says collection of all those elements of G that commutes with all the elements of G. Now, in order to prove that it is a subgroup of G, again we will take the help of one-step test. So it says the primary condition is that the center of G should be non-empty and it should be a subset of G first in order to use our one-step test. Now the question is, which element will always be there in center of the group? So we are in search of such element of group that will commute with every element of the group. And if you think properly, that element is actually nothing but the identity element, right? So I'll say as this Ex will be equal to Xc, whatever may be the element X in G, Ex will be X, right? And Xc will be X only. So whatever may be choice of X, this E will always commute with X, and this implies E belongs to center of G, and therefore center of G is non-empty. No issues for subsets. I'll say clearly the center of G will be a subset of G. Now again, in order to use one-step test, we should start with any two elements from the center. So we'll call that element as G1 and G2 respectively. So I will say let G1 and G2 belongs to center of G be any elements. Now since this G1 and G2 are in center, both G1 and G2 will commute with every element of G. So I will say G1x is equal to xg1, right? For all x belonging to G. So I should say xg1, okay, for all x belongs to G. And one more thing will happen, this G2x will be equal to xg2 for all x belongs to G. Now as we have to show G1 G2 inverse lies in center again, we need the condition in terms of G2 inverse as done in the case of center of element as well. So what I will do, I will pre and post multiply this equation by G2 inverse, right? And as discussed earlier, this is same as writing G2 inverse x will be equal to x G2 inverse for all x belongs to G. Okay, we'll call it as sum 2. Now as we have to show G1 G2 inverse lies in center of G, so we have to show G1 G2 inverse commutes with every element of G, and thus I am going to start with G1 G2 inverse x, where x can be any element of G, right? So I will say for any x belongs to G, I will start with this G1 G2 inverse x, which will be further equal to G1 G2 inverse x. This is simply by using associative property in group, which is further equal to G1. Remember, we already have the value of G2 inverse X now, that is same as X. G2 inverse, this is using 2, which is further equal to G1 X. G2 inverse again using associative property. Now which will be further equal to what? X G1, this is using what? Using 1. Now again using associative property, this is exactly same as X G1 G2 inverse. Therefore what we have shown is this G1 G2 inverse X is actually equal to X G1 G2 inverse for all X belongs to G, and therefore this G1 G2 inverse is a member of center of G, and therefore our center of G is a subgroup of G, and that is exactly what we wanted to prove.